Welcome to another recording of the academic webinar series. We'll get started right now. What you're seeing on the right-hand side of my desktop is some of the stuff we're going to talk about today. So I think the way to get the most use out of this hour in this webinar is for me to show you a lot of examples. And by showing you examples, I can show you things in JMP software that are really cool and helpful in understanding the concepts of ANOVA or the concepts of regression. So we're going to spend a lot of this hour in the software with data sets, actually exploring those tools. But before we dive into the software, I wanted to point out a couple of other really helpful teaching resources. So one of these resources is this thing called the Statistics Knowledge Portal. So I've got the link here. I'll show you this in a second, but I actually think it's probably a good idea if you take a screenshot right now so you can save these links for yourself in case I've got them hidden by other things as we're going through this session. So again, we're going to cover some stuff in the software in these first two sections, but a few resources that I've got here. The links are kind of long, so you're not going to want to have to type these out later. So the Statistics Knowledge Portal, if I go over to the website, you can get to the Statistics Knowledge Portal by typing Statistics Knowledge Portal or SKP and JMP into a Google browser. It will probably take you right here. Or you can get here from the main JMP webpage, jmp.com, and going to, I think it's Learn JMP. And this bottom option here, the Statistics Knowledge Portal. This is a really nice site specifically for ANOVA and regression. There's some really well-developed examples, nice interactive features to help you teach these concepts and for your students to go back and review the concepts. So when you land on that Statistics Knowledge Portal, you learn that we call it SKIP, which is hilarious because we call our software JMP, JMP, and so we're jumping and skipping, ha ha ha. So SKIP, the Statistics Knowledge Portal, is a nice place to direct your students to learn more about correlations, simple linear regression, multiple linear regression, one-way ANOVA, the t-test. And for example, let's just look at simple linear regression. There's a description of what we mean by simple linear regression. There's examples showing these different types of relationships that we can capture. There's a description here with extra interactive things that we can click on, describing what the equation is really telling us. So it's a really cool website. So this is definitely a resource I want you to know about. So in addition to the Statistics Knowledge Portal, there are a bunch of other resources linked in this document that you can get to in a variety of ways. You can go straight to this website here, or you can come to our JMP academic page, which is jmp.com/academic. When you type that in, it directs you to the country that you're in. I'm in the United States right now, so you're seeing mine customized to my location, but jmp.com/academic will take you to our academic main page. And if you want to find faculty resources, you're going to find them here in the faculty section. And under teaching resources in the middle. And this document that I'm going to show you is under the introductory statistics course material page. So if you want to teach with JMP and you want some special resources just for your course, this is a great place for you to come, is this course material library. And for the intro stats course materials, there's this linked document here, sample intro stats syllabus with JMP resources. So this document actually contains lots of the stuff I'm going to show you today. This document looks like this. It starts with some book options, books that either use JMP in the book or might have sample data set add-ins. Also, e-learning courses that you can get the materials from the JMP education team at SAS, or other e-learning courses you can ask your students to take or that you can take. So these are available if your school has a JMP license. These are available for free to professors and students at schools that have a JMP Academic Suite license. You also will find in this document the topic area and a bunch of resources related to that. So if I scroll down to ANOVA and regression, this document covers the typical topics you might find in an intro stats class, and so ANOVA and regression are the last topics typically covered in that kind of a class. So here under ANOVA, there are links to watching some short videos, more one-page guides and short videos in our learning library, hints about things in the sample data sets or in the sample data section of the JMP software that you can find that will help demonstrate concepts. Some suggestions on data sets. We're going to use a few of these, and I'm going to suggest some others as well. Case studies, which are maybe 5 to 15-page documents describing a real-world scenario and then asking students to do some analysis. And these case studies will cover ANOVA. And then for simple regression, again, links to some videos to help your students, pointing out some teaching resources built into the software, pointing out some data sets that are great for examples, pointing out the relevant case studies, and lab activities. There are also some lab activities available already developed. So this document is going to be a summary of a lot of those resources, and that's why I wanted to point that out to you. Some of those other resources, some of those resources that I just mentioned are those things that are going to help your student. And so you also definitely want to know about how to get directly to those. So they're linked from that document, but you can also go to jump.com/learn. And you'll find a bunch of topic areas. If we're looking at regression, we might be here, or if we're looking at inference on means, we might be here for ANOVA. So if we're looking at correlation and regression, here are a bunch of things related to correlation and regression. So for simple linear regression, we can watch this 2-minute video about simple linear regression showing an example. We can click on this 1-page guide and just save this as the crib sheet or the notes that we need to, as a student, to be able to repeat these things later. And links to some of those sections in the skip are here as well. So the 1-page guides look like this. They're 1 page. They always give you a sample data set to follow along if that's appropriate. And then you can follow the directions and see exactly how to create this simple linear regression using JMP software. So that was the 5-ish minute overview of lots of resources. One final resource I'll mention is there are also lecture videos online of a professor teaching with JMP. So Julian Paris works for JMP. He worked in the academic program for quite a long time and is a good friend of ours. And when he was teaching at UC San Diego, he created this flipped course where he gave his lectures in videos. The students could watch them on video, and then in class they would work on labs and assignments. So if you want to make use of his videos, you absolutely can. And so especially now, while many people are working from a distance environment, if you don't already have prepared high quality lecture videos, you're welcome to use Professor Paris. So to get to those, if we go back to the main academic page and go through the faculty and go through the teaching resources, we will land on this jump.com/courses page again. And here on online courses using JMP, this bottom link, significantly statistical methods, I also am giving you the direct link right here. So if you just screen capture that, you can have the direct link to it as well. And so this last resource I want to point out is a bunch of lecture videos showing how to understand these concepts and how to apply them in JMP. So for example, if you're teaching simple linear regression, here are things about the actual models behind the scenes, how to do those tests, how to use JMP to do this. And so there's a playlist on YouTube. There's other materials for this module that you can download for each of these. So the duration of all the videos for this course is a little over 15 hours. So lots of content here, and it's really nicely done. So again, you're welcome to use this in any way in your course. So again, I would suggest taking a screen capture of this little side panel if you want to have these references to get back to later. But what we're really going to spend this hour on is how to use the software to teach ANOVA and regression, and looking at example after example of sort of where those pitfalls are and how to cover the concepts using some of the built-in tools that are in JMP. Okay, so let's actually get into the software. Let's look at some examples and some of the cool tools for demonstrating concepts. Some of the examples that I'm suggesting, so I've suggested a few examples in that document, this intro stats syllabus document that I pulled up before. I have some of the same examples here and a couple other examples suggested as well. So I'm suggesting 4 data sets for covering t-tests. 3 data sets for covering ANOVA. 1 I threw in there for two-way ANOVA in case you're trying to get to that topic as well. A few data sets for regression, a couple things for combining ANOVA and regression into the same model. There's many more data sets that are appropriate for these topics. built into JMP and of course available all over the internet. But if you're looking for examples, I'm suggesting these. And you can find them really easily by being in JMP and going to the Help menu in JMP. And you'll see sample data in two places. You'll see it halfway down the list, it'll say sample data library. If I click on this, it's just an alphabetical listing of all the sample data sets. So you can find any of these data sets by name in this alphabetical listing. The other option, the bottom one that says sample data, this takes you to this thing that I already had open called the sample data index. And this actually indexes the sample data sets by the topic that we think that they're a good example of. So, for example, bivariate analysis, you'll find some these ANOVA suggestions here of height weight 12 and height weight 15. These are t-test examples. So these are nice examples of t-tests. So, for example, if I click on height weight 12, the data set looks like this. We've got gender, we've got height, and we've got weight for 63 students. And I'm going to pause again to tell you a good teaching tool is if you're teaching with JMP, you can turn on these little highlighters so you can circle things and help direct your students' attention to things. Sometimes it's a little bit tricky to know which spaces you're allowed to actually use. The way you do that is in JMP on a Mac, there is a JMP menu option here that has About JMP and Preferences. The Preferences is what we're looking for. So in Mac, it's JMP Preferences. In Windows, it's File Preferences. There are very few differences between Mac and Windows. This is one tiny difference. So JMP Preferences or File Preferences. If you go to the second thing down, Reports, there's this option for a laser pointer. When you install the software, it starts by being off and you can put it on in whatever color you prefer here. So putting this laser pointer on means that I can draw on output like this in JMP. So if you're a teacher and you're teaching anything in JMP, this is a really helpful tool. So again, it's JMP Preferences or File Preferences, and then it's the second option, the Reports, right here in the middle. So we've got gender, we've got height, we've got weight. The first thing I would do is look at a distribution of these variables just to explore them a little bit. So I can do that from the distribution menu. I can grab all three of them. Maybe I'll just look at histograms, no statistics. So I see the distribution of height is approximately normally distributed, the distribution of weight also approximately normally distributed, and slightly more males than females in the data set. If I click on males, I get that really cool JMP feature that everything is interactive. So when I click on the males, I see their data highlighted in the other distributions as well. So the males have still a normally distributed height distribution, males alone. The weight is still approximately normally distributed, but there's a little bit of bimodal. There's like a little cluster of heavier boys and a little cluster of, or a large cluster of lighter boys. For females, we're not seeing that quite as much. It's a little more uniform across the weight distribution and still approximately normal across the height distribution. I can also have that same interactivity by just grabbing and dragging my mouse and selecting some of the data in the height category and see how that's distributed across gender and across weight. So this is really fun to be able to interact with this way. So I always start by exploring the data with my students. Analyze distribution is one way to do that. Also starting in JMP 15, this little set of bars shows up here, this header graphs. If you click on this, it actually shows you that distribution output right there in the data table. Also interactive. So you don't even have to go to analyze distribution if you just wanted a quick summary picture of those distributions. Another tool for exploring the data ahead of time is the graph builder. Here maybe I want to look at we're going to start by thinking about like a t-test. So I might want to look at how the height is different by the males and females. So I can pull height into this axis. There's lots of ways I could look at this. I could put a box plot on top of it. And then I might want to split this out by gender. So I could put gender on the x-axis. As I get more and more variables that I want to explore, I can group things by another variable in the x direction or the y direction. I can overlay things on top of each other if I've got multiple groups I want to put on the same plot. I can color things differently. So there's lots of flexibility here, but to start with just a simple picture of females versus males on height, this is kind of helpful to me. It's a little hard for me to see, like to imagine horizontal lines across this space. So I may want to put some kind of grid lines in the background. If I double click on the axis, I did that very quickly. So I'm hovering my mouse over the axis. This is the axis I'd want the lines to emanate from. So this is the axis I'm hovering. If I double click, it's very busy. There's a lot of stuff going on here, but some of the cool things are I can add grid lines, and I'm seeing a preview over here. So when I add major grid lines, it adds a grid line across at every 5. It chose that by the increments of 5. If I wanted minor tick marks, I could add them here. If I put 4 tick marks between every 5, then it's actually marking off 61, 62, 63, 64, and then I've got a big mark at 65. I could add the minor grid lines as well. I could even add a reference value. So maybe let's look at what the mean is for all of the height. Well, it's not going to let me do this at the same time. I think that this 59.01 is what the mean is. We'll just pretend it is for now. We can go back and change this if we need to. I'll change the color. I'll say that this is the overall mean. We'll make it a little bit thicker by increasing this line style. I'll add this, and now you see it's going to label it overall mean and put a red line across my axis. So I'll say OK, and this is what my plot looks like right now. I'm labeling what I'm claiming as the overall mean, and then I've got the two groups. Kind of seems like maybe I'm wrong about that. So let's try again this distribution and see what the mean height is. 59.1. Yep. Okay. So that was the true overall mean. So we've got the overall mean labeled. So we can see that the medians of both groups are shifted slightly above the mean. That's interesting. So there's a little bit of skewness with tails toward the bottoms of the distributions. So that putting the grid in helps me to visualize this a little better and see this plot a little bit better. So maybe this is the final plot that I want. I can click in any of these boxes to change the titles. I can change the labels here. If I don't want to put height on there twice, I can double click here and ask for the legend settings, and I can maybe just choose the one with the dot next to it. Say that this was labeling the height. That's still not interesting. It's obviously the height. So maybe I don't want that at all. I can either check it off, or I can ask to not show the legend. So I'm kind of doing a lot of this very quickly because I'm very comfortable in JMP. I've been doing this for years now, and I know a lot of these tricks. If this feels a little fast or a little overwhelming, I really just want you to know that these things are possible. But even if you're brand new to JMP, you can still get a lot of great things really easily. So you can always tweak. By knowing JMP better, you can make all these little changes that improve things in some small way, but you can still get 80% of the way there with 3 steps instead of 20 steps. So if this feels a little bit like a lot of steps, then just pause, don't worry about it, and I'll go back to showing simple things in a second. Another option from this red triangle is this thing called redo. The column switcher under redo lets me swap out the height for any other variables that are similar in style, the type of variable to height. So I can have height versus gender on the plot, and then I can also look at the same plot with weight versus gender. It took away all my style elements. But I can use those same plots and switch out the column and explore multiple things in that same plot. Okay, we've explored the data. Now let's get to the t-test. So what we know of the data so far are that they reasonably fit the assumptions you'd need for a t-test. We don't have really highly skewed data. We don't have any really big problems. We have a similar number of males and females. We've got a large enough data set. So we meet the first conditions that we want to meet in order to even try using ANOVA. And then to do the ANOVA, I'll go to the Analyze menu, or the t-test in this case, and Fit Y by X is a really good place to start for this type of model. We can also use this Fit Model platform. Fit Model is where we want students to eventually end up. Fit Model will become very flexible and allow lots of other statistical models. But while we're only introducing ANOVA and regression, it's a little bit safer and easier to play in this box, the fit y by x. There are actually some extra features here that are specific to, because it's a simple context, we can do special things here. So if I choose fit y by x, I want, for example, the height to be compared between the two genders. So height is my response, gender is my x or factor. I can actually do 4 totally different kinds of analysis from this platform. In this case, I've got a continuous height variable, that's that blue triangle, so my response is continuous, so I'm in one of these. And then my factor is categorical, so I'm in this, so the intersection of that is I'm going to be in this one-way analysis sort of situation, so one-way ANOVA or a t-test. So I'll click OK. And this is not very exciting so far. All it did was show me the points for the females and for the males. So now I use the red triangle to do some more things. One of the things I could do is just, what are the means and standard deviations of the two groups? Another thing I could do is this t-test. So this t-test assumes unequal variances. It calculates the difference here. It's doing it in the order of males minus females. So if the difference is negative, that means which group is the larger. It means that females had to have been taller on average. If the difference is negative, then the second thing had to be bigger. So this difference of minus 0.62 means that in our data, on average, the females were 0.62 inches shorter than the males. We have a standard error for that difference. We have confidence limits for that difference, upper and lower. And notice that we include 0 in that confidence band. So if we're doing this by the confidence interval, we should know already that at the 0.05 level, we're not seeing statistically significant difference in height. We also get the t ratio that tells us how many standard deviations away from 0 we are in that standardized distribution. So this is assuming no difference in height between the men and women, and we are down here. We have women a little bit taller than men, but not very much taller. And it's not enough taller to actually become statistically significant. So we get 3 p-values here for the 3 possible tests we could be asking. This first one is the two-sided test. So that's what's showing here. It's coloring in the p-value that would happen from the underside, the lower side from our t-statistic, and the corresponding upper side. So that's 0.41. But if we just looked at the lower side, that's the bottom one, that would be half of our 0.41, so that's just 0.2, almost 0.21. And then the other p-value is from this point and up. So that's 0.79. So those are our 3 p-values for our 3 possible tests, but in any case, no matter which test we were looking at, we find nothing statistically significantly different here. We could also do this pooled t-test. So the first t-test we did assumed unequal variances. This one assumes equal variances. So this is the pooled t-test, and we see really similar results. So this one assumes equal variances. Those p-values are, if they're different at all, they're barely different. And that's because the pooled variance is a reasonable estimate. The two groups have similar variance between them. So this is the beginning of looking at ANOVA, is to compare two groups in a t-test like this. If we wanted to move on to an example that actually shows something statistically significantly different, we can also, I'll find us an example that works well for that. So the typing data is a nice example of an ANOVA where we'll actually find a difference. So I'll close this bivariate, and under this analysis of variance, we'll find this typing data. Or you can go to the sample data directory and get it alphabetically. So the typing data, the idea is that we have 3 typewriter brands, and then we are looking at the words per minute speed of typing. And we're going to see if one of these brands is easier for this typist to type more quickly. So there's actually a saved script already in this data table. If I were to click this little button, it would get me all the way to the results already. So this is a really cool tool. If you have students working in JMP, you can keep saving your work in JMP so that someone else can come later, or you can come later and repeat it. If we go to the Analyze and launch this ourselves, we'd go to fit y by x. Speed would be our response. Brand would be our factor. There's our 3 groups with no analysis so far. But we could start making a guess. Which groups do you think will be statistically significantly different from each other? Do you think Regal will be different from Speedy Type? Do you think Regal will be different from Word-O-Matic? And do you think Speedy Type and Word-O-Matic will be different? So then let's test that and see what the answer is. Again, I can ask for just the means and standard deviations of the groups, or I can go straight to this ANOVA analysis. My ANOVA analysis overall p-value tells me, yes, there is a difference between the groups. And here are the means for the 3 groups. Here are standard error for the mean for the 3 groups, but these are all using a pooled estimate of the error variance. So that means that for the Regal, this standard error of the mean, the standard error is created using the variance from all 3 groups. That's going to be a little bit different than when we calculate the standard error. I need to be able to scroll up just a little bit. So the means are identical coming out of the ANOVA analysis or just calculated from the groups. The means are the same, but the standard errors are slightly different. The standard error of the mean and the standard error of the mean here. These are slightly different because the standard errors here are calculated using a pooled variance and the standard errors here are per group. So this 0.81 is calculated only on the Regal data, these data here, whereas the pooled variance came from all of the data together. Okay, so here we've got the means. We know that there is something different. At least one of these typewriter brands results in a different speed than the others, but we don't yet know where the difference lies. So now we need to start thinking about doing the comparisons within the groups. So that's going to be comparing means. And if we don't want to, if we're still at the stage where we haven't taught our students about doing multiple comparison adjustments, we could start here by doing just the student's t-test. So this is individual t-tests on the 3 pairwise comparisons. So our 3 comparisons are Regal to Speedy Type, Regal to Word-O-Matic, and Speedy Type to Word-O-Matic. So 3 comparisons, and we're going to have to get an answer for each of those 3 t-tests. So down here, we get the results in 3 different ways. We get this threshold, we get this connecting letters, and we get this ordered difference report. 3 different ways to tell us exactly the same information. I find the ordered difference report to be really easy to interpret because it gives us p-values for those 3 comparisons. So I can see Speedy Type versus Word-O-Matic, this one was statistically significant. Speedy Type versus Regal, this one was statistically significant. Regal versus Word-O-Matic, nope, this one is not statistically significant. So if I go back up to the top to look at that, Speedy Type versus Regal was different, Speedy Type versus Word-O-Matic was different, but Regal and Word-O-Matic were not. And that's what these circles, this little snowman on the side, is telling us. If we start by clicking on the top circle, this is the circle that corresponds to the mean of Speedy Type. And this circle is completely separate from the other 2 circles, the circle for Regal and the circle for Word-O-Matic. When the circles are totally separate, they are statistically significantly different. When the circles overlap like Regal and Word-O-Matic do, then they're not statistically significantly different. So I can see this circle for Speedy Type, it's different than these 2, so those 2 comparisons are statistically significantly different, but these 2 overlap, not statistically significantly different. The means diamonds are also packed with information. The line across the middle is the actual mean for that group, and it corresponds with the mean, the middle of this circle. So that's the mean for this group. The top points are the 95% confidence interval for that group, and there are little points not quite at the corners, these little lines, and these lines are corresponding to, they're called overlap lines, and they correspond to if we had the same sample size in the Regal, the Speedy Type, and the Word-O-Matic groups. If they had the exact same sample size, then you could use these little lines as overlap lines to say if this overlap line does not overlap with this one, if there's no overlapping of those diamonds from that point on, then they're going to be statistically significantly different. But that's only true when the sample sizes are the same, so most of the time that little line is not that useful. The ANOVA itself will always be done with the pooled standard error. So in this example, there's no option for the unpooled t-test because we have 3 examples. So when we've got three groups, when we've got 3 or more groups, then we can't do just one t-test. Our first test will be an ANOVA, and we can follow it up with these paired t-tests. So from this point, from 3 groups on, any statistical software is going to be pushing you toward the pooled analysis. If you wanted to do an unpooled comparison, you could filter this and just look at 2 groups at a time, and then you'd have that option again. Okay, so yeah, let's look back at the results for the comparisons. So we didn't do control for multiple comparisons yet. We just did the raw t-tests, normal t-tests with no adjustment for multiple comparisons. So we're not actually doing this correctly yet. This is often how people will teach these methods. They'll start with a t-test, show ANOVA, show doing the t-tests within the ANOVA, and then you tell students, but we actually need to be correcting for the fact that we've got 3 tests instead of just 1, and so we shouldn't allow alpha to be 0.05 for those 3 tests. We should make it a little bit more stringent for each one so that we can maintain an overall ANOVA of alpha of 0.05 for the full experiment. So when we get to that stage, yes, we'll try a different method. So in a moment, I'll show you that. But this is just lots of ways of seeing the same information from just the raw unadjusted students t. So this ordered differences report is one way. It shows the unadjusted p-values. The connecting letters report is another way to see the same information. It tells you levels not connected by the same letter are significantly different. So Speedy type has an A, and neither of the other groups has an A. So Speedy type is different than Regal and Wordomatic. Regal and Wordomatic both have B, so they're not different from each other. So this is another way of saying exactly the same information. And here's a third way of saying the exact same information. This one says positive values show pairs of means that are significantly different. So this is negative. Here's a positive value. Here's a positive value. So Regal and Speedy type and Wordomatic and Speedy type are different. And then we see that same thing in the upper quadrant of this triangular, and so it's just redundant. So 3 ways of seeing the same results, and then a 4th way to see the same results. But if instead of looking at these with the student's t, we could choose a different method. So compare means, let's instead, I'm going to take off the student's t, and I'll put on the Tukey on a significant difference. If you want to compare all the possible pairwise comparisons, this is the best method to choose here. And when we hover, we see that it protects the overall error rate. So I click this one, and now my circles are a little bit wider than they were because it's harder to find significance, but I still actually end up with the same conclusion. So now my p-values are going to be a little bit different because these are the adjusted p-values. So you'll see the label at the top of the section tells you that this was using the Tukey-Cremier on a significant difference. And so all 3 of these ways of looking at the results are all after adjusting for this. We could also use another method. We could use compare means Sue's multiple comparison with the best. This would, instead of the Tukey, so now I've got them lined up next to each other. Sue's multiple comparison with the best reads across and says which one performed the best. Now I'll just do the comparisons with that one. So let's look at the results. So again, we've got these columns with positive values where we're looking for the mean significantly less than the one with the maximum. And then we've got a couple other tests as well. We've got comparison with a control, or this each pair with a stepwise adjustment. We also have non-parametric tests. So if instead of doing the traditional ANOVA, I want to do a non-parametric comparison, I can use the Wilcoxon test. So that's the same as the Mann-Whitney or the Kruskal-Wallis. I can use the median test. I can use the van der Waerden test. And I can use this non-parametric multiple comparisons for the follow-up comparisons. So there's a lot of stuff available in this menu. I also can test for equality of variances within the 3 groups. I can explore power analysis, a retrospective power analysis. Yeah, many, many, many options here. In addition, I can always apply a local data filter. So I could filter this data by brand, for example, and I could ask it to only look at this analysis for Regal versus Speedy type. So now it's actually going to do the pooled t-test instead of the full ANOVA, and you can see that it updated the output. We had run an ANOVA and it updated it to just do the pooled t-test for those two groups. So the filter, everything will update on the fly for the particular comparisons you're trying to make. So there are also suggested data sets for regression down here at the bottom. And I would recommend some of these are awesome. So this Anscombe data set is so great for beginning to talk about regression. Before I show you that one though, I'm actually going to show you another data set called fitness. So fitness has more variables in it. It might be a little overwhelming if it's the first time you're showing students data that's continuous, but we can kind of restrict our focus right now on these two variables. So what this data set is about is I like to pretend that I'm developing a competitor to Fitbit. If any of you have a Fitbit, they use a formula in the background to give you an estimate of what they call your cardiovascular fitness score. And some of the things that are going into that estimate are your weight and your resting heart rate that it's calculating if you've got a heart rate monitor on your Fitbit. So this is the same kind of idea. This oxygen uptake variable, this is like a cardiovascular fitness score. And in this case, the higher the better. Having more oxygen uptake means you have a healthier lung, a better ability to get the oxygen into your body. The run time is how fast you can run a mile, so how many minutes it takes you to run a mile. So nobody in this data set is winning any fastest human records, but there's some really respectable numbers in here, I say, as a 40-year-old who runs a 10-minute mile. So, so I think these are respectable numbers, but if you're a track star, these are a little bit higher than what you'd expect to see in real performance races. So this is like a typical sample of regular people. And we can look at the runtime as a predictor of that oxygen uptake, pretending that we're developing a new Fitbit or we're working on their algorithm and improving it and trying to see if we can help the oxygen uptake value get better, a better estimate of that. So to fit a regression, we still go back to fit y by x. Oxygen uptake is the response. The runtime is the factor. And now we're in this quadrant, continuous y, over here on this side, continuous x on the bottom, this quadrant. It's a regression type of analysis. It calls it bivariate here, but it's the idea is a regression. So here we see this relationship. So the slower you run a mile, the lower your oxygen uptake score. And we want to fit a line to that. So we're going to choose this fit line option. And it tells us here's the equation. Oxygen uptake y equals the intercept plus the slope times the x variable. We see those same pieces of information down here. So the intercept is 82.4, the slope is negative 3.3. We see p-values for those tests. We also see an ANOVA table, an overall ANOVA table here with this p-value that says something. One of the slopes in your model was significant. We only had one slope, so it's pretty clear which slope we're talking about here. It's going to be the runtime slope. Some of the things I like to show students here are to talk about what does this p-value mean. So the test for the intercept is testing, is the intercept actually 0? The intercept would be where this line crosses the y-axis when x is 0. So we have to first get x is 0 over to that corner of the plot. There we go. So when x is 0, where does the line cross the y-axis? It's going to be at 82.4. So that's what our intercept is. And the test of the intercept is this value actually 0? Should we really have the line going through 0 down here? And I think it's pretty obvious from this plot that no, absolutely not. This point should not happen down here. We can actually force a line to go through 0, 0. We can do that with this fit special option, where we can ask it to constrain the intercept to 0, or we can force the slope to be a certain number. When I constrain the intercept to 0, then I see there's my 0, 0. I get a very different fit, and it's obviously it's a terrible idea. This is not the right line at all. So it's no surprise that our p-value here is statistically significant, telling us, nope, 82 is not close enough to 0 to possibly be 0. The next p-value, this one, our test of our slope, is testing, is the slope equal to 0? So is it possible that actually we want just a flat line through this? And I can show you what the flat line would look like by doing this fit mean. The flat line would look like this blue line. So is it possible, we fit the red line, is it possible that the slope of the red line should actually just be flat like the blue line? And our p-value says nope. That's so rare, it's so unlikely to have seen this slope with this type of data. We don't think it really should have been flat. We think there really is a slope here, and it happens to be a negative slope. So every time we increase runtime by 1 minute, so every time if it takes me a minute longer to run this mile than it takes you, on average, then we should expect that on average, so for all the people that run a mile in a minute longer, they're all going to have approximately 3.3 lower score on their oxygen uptake. What else might we want to do here? I'm going to remove some of these crazy things that I've fit by going to the bottom and remove fit. Some other cool things I can add to that linear fit. Let me maybe zoom back in on it. So I'm just grabbing the bottom corner and stretching to get this plot to look more like I want it to look again. Oh, that's better. And now from this linear fit, some other stuff I can do is I can ask to plot the residuals. This gives me a sense of the typical plots I look at to assess if I meet my conditions. I really want a cloud of points around this centered line. I pretty much have that. These guys don't have the same variability that I see in this part of the plot. However, it's just because there's just 4 points out here. So I'm not worried about this. I would always be worried if I see a fanning out of this variance, but that's not really what's happening here. It's really just we don't have a lot of data over here. We have a lot more data to be able to see the spread in this region. So I might want to keep an eye on these points if I really wanted to fit the model with them and without them and see if there's something dramatic. But truly, these residual plots look pretty good. I'm not concerned about these. And then for the quantile plot, again, everything is within those confidence bands. So this looks great to me. This is a lovely example. Seems reasonable. So now that I've decided, yes, my model fits well, I guess one more thing I should look at is the R squared. The R squared is the correlation squared, and the interpretation of this is how much of the variation in Y, or oxygen uptake, I'm able to explain by my X, or runtime. So runtime, if I know your runtime, I'm able to explain 74% of the variation in your oxygen uptake. I can get kind of close to a reasonable prediction just by knowing your runtime, but there's still a lot of information I don't know. So from this little linear fit, we can do things like put the confidence curve of the fit or the individual. You'll see these twice: confidence curves fit, confidence curves individual, confidence shaded fit, confidence shaded individual. Let's put on the curve fit first. That put little dotted lines for the confidence band. Now let's do the other one, confidence shaded fit. That shades it in. So I usually just don't put the dotted line on and just put the shaded. Then we also have that individual. If I put the shaded for the individual, what I'm seeing is this skinnier part is the confidence interval for the mean. The fatter part is the confidence interval for any new predicted value. So the mean means if I take a new set of 20 people and I find that 20 people have a runtime, an average mile run of 12 minutes, then for those 20 people, the average I should expect is, let's see if we can crosshairs this. So if your average runtime is about 12 minutes, then on average, I expect your oxygen uptake to be 43.3. And then there's a little tiny confidence band, so it's 43.3 is the mean, but that confidence band goes up to 44.5 and down to 41.2. So I'm reading the little confidence interval around that mean value. So this confidence band is the mean expected at this value. The prediction interval is this longer the wider interval, and that's for any one new person who has a runtime of 12. So not thinking about it in terms of means, but just anybody who walks in the door and happens to have a runtime of 12. Now I need to be a little bit broader about guessing their true oxygen uptake. I can also save those values out. I can save out the predictive values, the residuals. I can save out the confidence limit formula for the mean or for the individual prediction. And if I save these, they drop into my data table, and then I can use them in other plots. So there's lots of cool things I can do here. In addition to fitting just the linear fit, let's take off this part and this part. I can also fit other shapes here. So if I wanted to fit, for example, a quadratic, now I see the quadratic superimposed in this orangey color. Maybe I need to take the confidence curves off totally. So there, our red line was our linear fit, our orange is our quadratic fit. I can check the R-squareds and see, did the quadratic get any better? Let me hide some of this stuff. And it looks like our quadratic has a tiny increase in R-squared, but barely anything. It also looks like our quadratic has a non-significant quadratic term. So it doesn't seem like that's adding much to the model. So the quadratic's a bad idea. Let's take that one back off. Other things we could fit are if we believe that we should do a transformation, we can have it do the transformation in place and back transform it. So maybe I'll do a log-log transformation, and then it shows it back transformed into the real data. Here's the log equation that was estimated, but it actually shows us back to the original scale. We could also add a spline effect. So there's really cool things we could do. We could fit a spline here. I can pick any of these values. And then I get this little alpha or lambda smoother. So I can make it really spliney, overfitting the data, or I can make it completely flat where it matches the regression line. So as I add a little curvature, I can start seeing maybe some kind of a cubic effect is what I really want to fit here. So then I could go back in and I could fit a cubic. And our cubic is now this yellow one, and it's also not going to be dramatically different. So we've got all this flexibility to try lots of different things here in place. And we can do some of the same stuff over here in Graph Builder. If we put oxygen uptake as the Y and we put runtime as the X, we can also fit things here. So if I try to fit a line, I'll take the smoother back off. If I fit a line, there's lots of options for how I fit that line. I could put the equation up on top. I could put the R-squared on top. I could even put the F-test on top. I can put that prediction band as well. I could put the root mean square error on top. I don't want all of this stuff. I'm going to take maybe just these things. But instead of fitting a linear, I could fit a quadratic, or I could fit a cubic, and just do that in place in Graph Builder. So this is a lot of fun to be able to see the different ways in JMP that you can do this. You're getting exactly the same plot, exactly the same information, but you're seeing it in a different way. And as you can see, Graph Builder is a little bit more specialized to make really nice, stunning graphics. So this fit Y by X is really practical, but if you wanted to make publication quality graphics, Graph Builder is going to be a little bit more flexible and give you more cool things you can do. Okay, we've got about 5 more minutes, so I want to think what's the most important other things I should show you. When you do get ready to move out of fit Y by X, you'll move into fit model to fit things with more than one X variable. So if we wanted to predict oxygen uptake with sex and runtime, I can add them both to the model and run the model. And now you see that I'm getting 2 lines. I'm getting a line for females and a line for males. And if I look at the parameter estimates, I'm getting an intercept, I'm getting an effect that has to do with the sex, and I'm getting a slope for runtime. But you can see that this is actually forcing the 2 lines to be with the same slope. It allows different intercepts, but the same slope. So I really enjoy using this to show students what the meaning of an interaction term is. So really what we want to fit here is oxygen uptake with sex and runtime. I want to add these effects, and I also want to do the cross between sex and runtime. So their interaction. So I want the sex effect to be their 2 different intercepts. I want the runtime to be a slope, and then I want the sex by runtime to allow the slopes to be different for the two different sexes. And when I run this, you can see I now am allowed two different slopes. So you can compare really easily what you're getting as you add new terms into your model. And again, we get lots of plots and things to explore here, lots more options up here from the red triangle, more things we can do and so on. So there's endless stuff that we could talk about here, but I did want to show you that. And as your very last nugget, these teaching scripts are really cool. So in the sample data index, we were using this to find data sets, but we can also use this for these really cool teaching resources. So under this teaching scripts, there are some really nice things in the interactive teaching modules. If you need to help explain to your students the sampling distribution of sample means, how there's an underlying population, and then you take one sample. From that sample, you get its sample mean of 100.18 in this case. So you drop that sample mean into this distribution of sample means. So right now we've just got one thing in it, no standard deviation, because there's no standard deviation defined until you've got at least two observations. So let's add another one. So now we've got two sample means in the distribution of sample means. Let's draw another one and another one and another one. And let's draw 95 more. So we get a total of 100. And so here we are drawing sample after sample, adding the mean from the sample into our distribution of sample means, building this distribution. And so we can see that the distribution of sample means does sort of become normally distributed, much tighter variation than the original sample or than the original population. And we can really talk through the what's happening in the background. So there's a bunch of these for developing as you're going through confidence intervals and hypothesis tests, and then demonstrate regression and demonstrate ANOVA hit it home for those final, now you're going to fit a regression. Well, here's our little picture of sample data. I could make the intercept be lower or higher. I could make the slope be flatter or steeper. I could make the correlation be less or more. I could rename the response and the predictor. I could change where the mean, to rescale this data. And then I can do things with it, like I can fit a line, where I try to fit a line to this data. That did not work. And I'm just adding points. So I'm doing a terrible job with this because I recentered it. Let's open it again. So not recentering it this time, just using it right away to fit my line. I get these little boxes. I click in the box to move this line around. So I'm going to try to get this line to match up as well as possible. So here's my guess. I'm seeing the residuals over here in the plot. And now I can ask it to fit my residuals. So it draws a little line direct from the point down to the line. And then I can show my squares. Now it turns them all into squares, adds them up. So here's the sum of squares of all those residuals. And then I can compare this to what if I fit the real least squares line, and there's its sum of squares error. So I didn't do too bad. I only had a little extra error compared to the real line. So lots of cool things here in this interactive teaching modules and teaching demonstrations. And then one last point for regression, there are also 3 data sets that really illustrate cool concepts. The Anscombe, if you click on this, you'll see 4 conditions that look identical. Same R squared, same parameters for the model, but when you put the points onto the plots, you see very different scenarios. So this is a nice way to illustrate how important it is to visualize your data, because if you just look at the statistics, they're all identical. So that's a nice one. Also, the row data set. This data set has a high leverage point. So if you get into multiple regression, this is a really interesting data set for showing what a leverage point can do. The slope data set is a really cool data set for showing why you might want to visualize data. This one, if we put y in for y and x in for x, looks like I'm going to fit the line this way. When I fit the line, what the heck happened? What a surprise. And it turns out this is because there's a lot of data stacked on top of each other here. So if I put this density on top, you can see there's actually a ton of repeated data in this region. So that's why that happens. So those are just some final points. It is a minute after 3 o'clock, so I definitely need to wrap up. You are welcome to send me questions at ruth.hummel@jump.com. Thanks for watching. You can find more recorded webinars or sign up for live academic webinars at this website. Hope to see you again.